Hey everyone, this is our November webinar, and today we're talking about harmonic problems, how to fix them, or how to identify them and fix them quickly and cheaply. It just sounds crazy to me. I just never believed in this stuff, and I think at the end of this I'm going to be a believer. So Dwayne wrote a paper on this in the International Journal of Energy Management this year, right? I think it was published this last year.
Yes.
I don't know which issue it was in. Yeah. And so anyway, so Dwayne Warren, you can go to the next slide, he works at Jones Lang LaSalle. He will introduce himself, but one thing I'll mention about him is he loves to teach. He loves to teach. That's what I've learned. And yeah, and he teaches very clearly. He doesn't use all these big words, not too much jargon, makes it simple. So I really appreciate that. I'm going to take my camera off and I'm going to leave, and you're going to, I'm not going to leave, I'll be here, but and you're going to take over, and I'll be back for questions a little bit later. So take it away.
Thanks. So as John indicated, I'm a Texan. I'm going to talk a little bit about myself for a couple of minutes. I'm the engineering director in the Energy and Sustainability Group at JLL, and I do some field commissioning work, also supervise the engineering work for about 15 or so commissioning people. I've worked in California for 10 years. I'm in Texas for the last 12. I was originally born in Canada, so you might hear that in my accent from time to time. I won an award this year for energy innovation with AE. I'm an international award winner. And I've got patents, and I've got a patent and trademark. I do some mechanical commissioning, fair amount of BMS testing and consulting, electrical harmonic analysis. I started out in life as a refrigeration mechanic after going through college. And so I've got a mechanical engineering degree, and I went, because I was bored for a little while, I went back and got a degree in industrial electronics. So I understand electronics very, very intimately. So this is sort of an extension of an internal presentation that I did for our company, and there's a little more meat in this one. So you're going to see bits and pieces of the JLL logo from time to time. Why should you care about it? So harmonics are an easy way to cut costs of building, relatively simple to analyze, it's pretty simple to monitor, do a little bit of math with each utility bill. It does affect the power bill, and I'll explain why in a minute, but it can affect the power bill by as much as 30%. And it's a real bummer when that's happening. It's pretty easy to fix, and that's good news when you fix it, but 30% is a lot. And you're going to find some surprising sources of it. It does affect equipment lifespan. Harmonic and transient energy will burn out transformers quickly. Typically a transformer, you might get 20 or 25 years out of it. If you have a pretty high harmonic load in 30% range, you might only get 5 to 7 years out of that transformer, maybe even less. So, and it'll cause nuisance breaker trips, it'll cause issues with wiring, can burn out the grounding grid, things like that. Might cause problems with X-ray equipment, radiology equipment, might cause problems with elevators. So it's a problem. Harmonics are a problem. And what we want to do, we'll talk about where they come from and how they're generated, but for now I just want to talk about what's the first thing you do. And so if I was looking at a facility, the first thing I would do is I would say, hey, I want to see your utility bill, and I want to get billing dates, and I want to know the consumption and the demand. And I'm going to do a little bit of work in Excel to determine something called load factor. And load factor is what's the average hourly consumption for each month. So I take the consumption for that month, I divide it by the billing days in that billing period and divide it by 24 hours in a day. And I divide that number there by the demand for the month, kVA demand or kW demand. And so we end up with a chart that looks kind of like this. And this is actually taken from a data center. And you can see that for this data center, that their load factor is just slightly under 1, which you know, for a data center of that age, this one is 20 years old or so, really should be around 0.75. So it's elevated. That's telling me I've got a pretty high consumption number for some reason. And you notice that in 1 month, in June of 2024, it goes over 1. Well, that's impossible. That's basically saying that my consumption is higher than the demand. And that's just impossible. Can't have that. And really, in the real world, I start to get a little suspicious when I see it over 0.8. So these are the numbers that we look for. So below 0.65, you might have a power factor problem or maybe a DAN limiting issue. I want to look for low power factor values. Between 0.65 and 0.8, it should be okay, but when it gets above 0.75, I start to get, you know, I get itchy and I start to shuffle around my seat a little bit. And between 0.8 and 0.95, you likely have a harmonic problem. When you get up above, definitely when you get up above 0.9, there's a harmonic issue in the building somewhere. And what happens with it, why it's a problem, is that basically you're feeding electricity into the building, and there's equipment in the building that is producing a transient or a harmonic piece of harmonic energy, and that is acting like a broadcaster inside the building. The theory used to be, because there was so little of it in the building, and when I say used to be, I'm talking back when Elvis was around, it used to be that harmonic energy would get dissipated inside the building. There's so much of it right now, and there's been some changes in wiring practices that now that radiated harmonic energy will very often find its way back down the main feeder, go right to the meter, and the meter is just a counting device. It doesn't care which way the power is going; it just counts it. And so it counts that energy and looks at it as basically as energy that's being fed into the building, or energy it counts it as energy that's going through the meter. That's the right way to put that. So you paid for it going in, the equipment does some stuff, generates a signal, goes back to the meter looks at it and goes, hey, I'm going to count that. Does a very good job of counting it. Most meters do a very good job of counting it. And this is not power factor. It is not. This is something else completely. It is a harmonic signal that's being generated inside the building. So there's a few notes about this. Older buildings tend to have lower load factors, older office buildings and things like that. Data centers typically tend to have a harmonic issue. Usually it's because of the inverters who are then generating a transient and a harmonic and various other things that are kind of not very healthy. Sometimes the servers will do it themselves. That can be an issue as well. Newer buildings typically tend to have more harmonic issues. That's because they have larger VFDs in them, some on the chillers, some on the motors, things of that nature. And less expensive VFDs tend to generate more harmonics, and that's a fact. They don't have filters on them. They don't have any sort of capture circuits or regenerative circuits or things like that, and so that harmonic gets generated, and it'll either go back into the system or it'll go in the ground, or usually it's fed back into the system. It's usually the way that it winds up going. We're going to talk a little bit later on about neutral and ground currents, but it causes a problem with neutral currents tend to really overheat transformers. Ground currents can cause problems that you can actually burn out the grounding rod or grounding grid in the building. That's a real bad problem when that occurs. Very expensive to fix, and it creates a condition that's actually an ungrounded electrical system is actually quite dangerous. Relatively easy to fix. You can use input line reactors or ferrite chokes. I'll talk about them in a minute. There's that warning again, not power factor. So I made a little conductor here. And what you got in the middle of the conductor is you got the 60 hertz waveform. And what's happening is from one one copper atom to another, the electron is moving back and forth. Copper works pretty good because it's got one spare electron in its outer layer, in its valence layer. So it just moves back and forth. Those electrons move back and forth from one atom to another, transferring voltage. And when you have a harmonic, the regular 60 hertz signal gets squeezed into the middle 2/3 of the conductor. And you can see the other harmonics, which are third harmonic, fifth, and seventh, which are 3 times 60 hertz, 5 times 60 hertz, and 7 times 60 hertz. And you can see them getting pushed to the outside of the conductor. So think about that conductor for a minute. It's a solid piece of copper, and what's happening is the electrons inside that copper are moving back and forth at different rates down the length of the copper conductor. Not surprisingly, what happens to that conductor is it tends to physically vibrate. And that's the buzzing sound you hear when there's a high harmonic. And I can actually replicate that. If I take a third, a fifth, and a seventh harmonic, I can make that sound, and it sounds exactly like the annoying buzzing that you hear sometimes in electrical rooms. Every once in a while, you're going to see that the electrons sort of line up with one another there. And when that happens, because it's happening 60 times a second, because that's the primary waveform speed, that energy inside that conductor spikes, and when it spikes, it creates a spike in the magnetic field around the conductor. That's very handy for us from a measurement point of view. I'm going to talk about that in a minute. Of course, this also heats up the conductor, as you can imagine. You're doing some physical damage to the conductor itself, so it heats it up. And it heats up the transformer, heats up the starters, heats up contactors. Everything gets heated up by this weird sort of motion. It's not really useful energy. Harmonic, it doesn't do an awful lot of work because it's all of the devices that are in the system are made to operate with the 60 hertz waveform. So it kind of just runs back and forth and annoys everybody. So there's an initial waveform, blue line, 60 hertz waveform. And you can see there's a third, a fifth, and a seventh harmonic. What happens with those is that when you add up all that energy, it produces a waveform that looks sort of flattened on the top. And that's the red line that you see. It does another thing that I just want to point out to you. If you looked at it on an oscilloscope or a piezometer or something like that, it'll look like that. You get a waveform that looks like that. It'll be flattened on the top for some reason, in some ways. But the other thing it does is this is a 3-phase waveform. It increases in neutral current, and you can see right there that there's an awful lot of neutral current in this conductor. That's the same 3-phase waveform with the neutral bus and the neutral current in it. And normally in a neutral line, you might have 2 or 3 amps or something like that. On a large circuit, maybe you have 5 amps once in a while. But if you have if you've got 30% harmonic, you might have 70 or 80 amps inside the neutral line. Not good at all. Don't want to see that at all. Very hard in the transformer. So high neutral bus currents are hard on transformers. They'll shorten the lifespan drastically. Can create a safety hazard. High ground currents, same thing, bad on transformers. Definitely going to make a safety hazard. Both of those will cause problems with the BMS because the BMS is getting these weird voltage signals and the ground is not very stable and things like that. So the BMS, fire alarm, elevators, all that stuff that requires a reasonably good sensitive ground is now going to have a floating ground, and it's going to tend to operate erratically. Does increase the utility bill. And now the point number 5, love point number 5. PD systems generate, some of them generate a significant amount of harmonic energy. It's not unusual for a 1 meg PD system that has sort of middle of the road inverters on them to generate as much as 200 kilowatts, or maybe even as much as 300 kilowatts of harmonic energy. So what happens when you do that is that you turn on the array, and the array puts out 1 meg, and you're looking at it and looks like it's okay. Maybe it's somewhere between 900 kilowatts and a meg. But for some reason, when you turn it on, the building energy use goes up by about 200 or 300 kilowatts. And you can't really understand why that's happening. So, well, it's because the harmonic from the array is going back into the main service, and the meter is counting it. So we do want to be aware of that, and you can see that when you turn the array on and off, you can watch the power use go up and down. So the field measurements are pretty easy. We're going to talk about that in a minute. I can tell you that data centers usually have harmonic issues. Newer buildings do too. Less expensive VFDs, talked about that before, they will generate a harmonic. And it can cause issues in the system. So if you suspect a harmonic, this is the meter that we use. So this is an EM meter, and it's an electromagnetic meter. It's the same sort of thing you would use for measuring EM radiation on anything, really. You remember earlier from the earlier graphic where I showed that the harmonic energy got pushed out to the outside of the conductor? Well, when that happens, it makes the magnetic field around the conductor a lot stronger. And so this gives us a chance to do a guilt-free way, a fairly quick and easy way to see whether or not you have a harmonic present in your building or in your system. And so we use this is a triple axis, so it allows us to measure in any direction and allows us to measure magnetic field readings at different parts of the system. So I don't open up the MCC, I don't take covers off equipment. I just use this to measure the magnetic field, the milligauss readings. Don't open the cabinets up, don't do that. Might need to do it later. If you want to confirm something, you might need to put in a power quality analyzer, but this is a good way to just measure that. So less than 200 milligauss, nothing to worry about. You probably have 5% harmonics or less, not worth chasing down. More than 500 milligauss, there's likely a 10% harmonic, maybe as much as 15%. And you may see values go up as 3,500 milligauss. That's very problematic. Not going to be harmful to your health. You're not going to, grow an extra arm or anything like that if you're around it. But 3,500 milligauss is indicating that there's a serious harmonic or transient problem. And now what you're going to have to do when you find this is you're going to have to just do some other checking on that MCC and see where that energy goes. Normally what I do is I normally start at the meter to see whether or not, or the main transformer to see whether or not that energy is present there. If it's present there, I start working my way backwards through the MCCs to figure out which piece of equipment or pieces of equipment are causing a problem. And I'm going to look for things like chillers. I'm going to look for PV systems. I'm going to look for inverters. I might look for UPS devices. I'm also going to look at lighting systems because LED lights tend to generate a fair amount of harmonics. Some of the cheaper ones do. And so when I find those panels or those devices, then I'm going to isolate that, and I'm going to say, okay, well, the problem is likely here. And now we're going to talk a little bit. Let's make sure I get the slide or in the right order here. Fixes. Perfect. Lots of different ways to treat a harmonic. And one of the ways are there's a passive way, and that's an input line reactor, which is basically a specific type of transformer that it's only half of the transformer. It's got a lot of wire in the winding, and those wires are designed, and the whole thing is designed for that magnetic field, that stronger magnetic field, to get a crimp put in it and basically slow it down, slow down the magnetic field. And one of the things about a harmonic is that if it's present in the wire, it creates a stronger magnetic field. If you can affect that magnetic field, you will basically reduce the harmonic. You'll convert that harmonic energy into heat, and that's what an input line reactor does. It reduces that magnetic field to a point that it's normal for a 60 hertz signal, and when it reduces it, it converts that energy into heat. You could use an active filter. Active filters are basically like hockey goaltenders, and they read the harmonic or transient signal coming in and produce a invert signal or inverse signal to that to cancel it out. Input line reactors have a fairly good lifespan, much like a transformer, 15, 20 years. Active filters don't. They typically don't have that kind of lifespan. They're usually in the 5 to 7 year range. And I would just say that it's, you know, a regular AC signal is 60 cycles a second. A seventh harmonic or fifth harmonic, which is the one that's really harmful to circuits, a fifth harmonic is moving at 300 cycles a second. That's pretty quick. And if you're going to generate a inverse signal to that, and remember that harmonic signal is sort of, the amplitude is kind of moving up and down. It might not be exactly a fifth harmonic. It might be 4.9, might be 5.1. It kind of wavers around. That active filter has to do all of that at a rate of 300 times a second. That's awfully hard. I'm not saying it's impossible, but it's just awfully hard. And so it's going to be, with a lot of harmonic noise in the system, an active filter may not be the best choice. And then we come to ferrite chokes, my favorite. So ferrite chokes are basically a round iron core, round piece of iron. It's an iron core basically. It's hinged and allows you to open it up and clamp it around the conductor. And same thing as the input line reactor. It acts on the magnetic field in the conductor, and it reduces the amplitude of that magnetic field. Of course, when it does that, it cuts into the energy generated by the harmonic that's creating that bigger magnetic field. So the ferrite choke will warm up a little bit. It might get up to 100 degrees or 105. It won't go to 110. It'll just be a little warmer. And they are insulated, so they just clamp. It's a three-phase device. You clamp one on each conductor, and away you go. You may have to, depending on the amount of harmonic, you might have to put a couple on there. I've never had to put 3 on, but you might have to put a couple on. If it's a large chiller, you might have to put a couple of ferrite chokes on there. Ferrite chokes cost the big ones cost like about $150 a pop. You can buy lots of them, lots of the smaller ones for, $100 a pop. They're pretty inexpensive. Input line reactors for something like a 1,000-ton chiller, input line reactor for that is probably, by comparison, is probably $15,000, something like that. An active filter is significantly more expensive. It might be 3 times that. It might be 50 grand. So I like ferrite chokes for that reason. They're used in cell phone towers all over the place. Ferrite chokes are used everywhere to deal with harmonics, and it's low tech. The only thing that I would say, when you put them in the panel, you have to label them, and you have to label the panel and say there's a ferrite choke in here, and it's to deal with harmonics, and that's to prevent people from opening the panel up at some point and removing it because they don't understand what it is. I would recommend on equipment, especially new construction, and if you're doing a retrofit, if you're going to install a VFD, use VFD rated wire. It's just something you need to do. It's going to have the wire bundle's got an upgraded ground. It's got a really good shield in it. Neutral wire is very well insulated. and the ground is insulated as well, and it actually is quite a bit larger. And the shield, there's internal shields on those as well. And so then that increased energy created by the harmonic is going to be absorbed by that shield, and then it'll just kind of make that problem go away. Belden makes pretty good cable like that, and so do the other manufacturers, VFD rated wire. Anybody have any questions?
Yeah, we got some. But first off, can you show us what a choke looks like? And maybe, do you have a picture of a panel with chokes in them?
Sure, choke. I'm just trying to pull up a picture of it here. You can buy them on Amazon, believe it or not, but those are the smaller ones. And if I was going to do a lighting panel, I would just buy the ones on Amazon. They're like, 10 or 15, 10. You can get like 5 for $15 or something. So there you go. They pop open and the conductor goes inside. They've got a little hinge on them and they're insulated.
They look like CTs, except for they're not connected to anything. They're just
right.
Yeah.
Yeah. It's a hunk of iron, and if you wanted to get kind of highly technical about it, this is really how transformers are made. It's also how permanent, if you want to go to a junkyard and somebody's got a magnet that they're using to lift cars up with, this is one of the bases. It's part of that device. This is just the iron conductor, and all it's doing, since there's no other conductor in there, it's just the one conductor. It's just taking that magnetic field and it's turning it into heat. And a nice surface area, does a very nice job.
All right, so these are super cheap solutions. So now so I want to go back over what you said, because there's a part here that I'm missing. And so step one, calculate the load factor. If it seems really high, then we might have a harmonic problem, and then we can do the next step, which was to get a Gauss meter and measure at the motor control panel. There it is. Measure how many milligauss it is, and if it's high, then maybe we have an issue. Now you said, but the next step is where I got lost. Then you said, okay, let's say it's really high, it's maybe 1,000 milligauss, and then you said, then you trace it back. What do you mean by that? So we didn't open the panel in the first place. What do you mean trace it back? Do you mean go to a chiller panel, which is a sub panel? Is that what you mean?
Yep. We would. So if I went to the primary meter, I'd find out, hey, is this primary meter being exposed to harmonic? And okay, it is. So now I'm going to go look at the MCCs in the building. Which MCC is causing this? And then as I look, when I'm at the MCC, I'm going to take this meter and just run it down the front of the panel, and look at the circuit and look at the reading. And these meters take about a second or two to respond. So you want to 1001, 1002, 1003, and you'll see the number pop up if there is a problem. So and then from that, I'll want to see where the equipment is that's causing the issue. And we are looking, when we look at this, we say, hey, we're going to put the correction inside the MCC. And when we do that, because there's enough wire inside of there usually, number one. Number two, I can put a label on the MCC and say, hey, there's something going on here. And then number three, if it's there and an electrician looks at it, chances are he's probably going to understand what it is. Yeah. If it's sticking inside a chiller panel, you never know about those chiller guys. They kind of do crazy things. So I'm going to bring this up because I bought it a few times. This is on Amazon. That's the same meter.
It's only $158. I didn't realize that. I thought those were expensive. Okay.
Yeah. It's kind of, and there's several different kinds out there. I like this one from Amazon because it's available and they ship it right away. But you can go crazy and spend $300 on one, but that's as expensive as they get. So
Okay. Oh, here's another question. Now, and I'll go back to the questions in a minute. So I walked through data centers, and I think I talked to you on the phone about this. You know, I was in the FBI data center, the big one, and I remember walking through all the servers, and it felt like, I don't think it was true, but it felt like all the skin, you know, all the hair on my arms was sticking straight out. I don't think it was, but it felt that way, and my body felt really strange for hours afterward. Now, was that magnetic? Did I feel a
Like,
magnetic field, or what was I responding to?
yeah, likely you were. Servers
So that
generate a pretty high harmonic.
so
Did
so
you?
that was that. So then the Gauss meter would have been super high. The reading
Right.
in there would have been really high. Okay,
So do you have a laptop in front of you right now?
right, of course.
It has 3 million transistors in it.
Huh.
And
Okay.
a server has close to 50 times that number. Each one of those generating a small amount of harmonic energy. And yeah, sometimes they cancel one another out, but let's get real. 50 million or 150 million transistors are not going to be singing in harmony, canceling out each other's harmonic. It ain't going to happen. So they generate it, and in theory, it's supposed to go to ground, but very seldom does it ever. So,
Here's a simple question. Suppose you were an ESCO and you're looking for ECMs. Um, could you just say, we're gonna, it's a data, we have a data center in this college or in this hospital or something. It's kind of big. And we're just gonna assume that we can reduce the power in this meter by 10%, and we're just gonna do it. We're not even gonna measure anything. That's kind of stupid, right? I guess you should probably measure the Gauss and trace it all back.
I
But
would.
see,
So,
you still can't estimate what the savings are gonna be until you do the savings. That's the
so here's
thing.
what we do when we're going through this right now. Initially, when we do our first walkthrough, so we are gonna come on now. Let's go back, go back, go back, go back. Oh, check the results. Went too far. Got a little too crazy. We're gonna take that chart,
The,
and what we're gonna do is we're gonna say we think a reasonable load factor is 0.75. You're up
and then,
around you're up
okay.
you're up around 1. The difference between those two is where we think the squeeze is, and we think maybe the reasonable value is 0.75, so we're going to take you down to 0.78. And what does that mean? This is a data center, and they have several thousand amps going through it, so it's a significant deal. So
But on your load factor equation, you're using kilowatt hours and kilowatts. Are both of those going to be affected, or only the kilowatt hours by putting on these chokes?
that is a very, very excellent question, and very, 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 very excellent and very, very smart. And I will tell you that the way power meters work is that they are very, very, very picky and very exacting about measuring each last micro piece of a kilowatt hour. That's done for a number of reasons, because when they first came out, they were pretty sloppy and they didn't do a very good job of it. It very much does affect the kW reading, the kilowatt hours. That harmonic does affect that. The kVA is really, it really doesn't affect that. The way the meter reads it, it's an
Okay.
average, and
Okay.
it kind of misses all that stuff. It's just not made to do that.
Okay. So
Um,
then you're going to reduce your power factor from this high level of 0.95 to maybe you think it should be 0.75. And then
right,
you'll back engineer, this is how many kilowatt hours will be saved. We're not going to change the demand at all. This many kilowatt hours will be saved. And that's how you can make this estimate of what you could save. That's
right, yeah,
interesting. Okay. That's cool.
right.
Um,
Now on paper, you may actually also improve their power factor slightly, right? Because that's power factor. That's how power factor It kind of depends on the meter that's used. So some meters actually read kilowatt hours, read kVA, and do some math. The older ones do that. The newer ones don't do that. They look at phase angle and they calculate power factor directly from the phase angle. And so, you'll correct this problem, you'll save some kilowatt hours, and it won't affect the demand. Won't affect power factor. Won't affect it at
Okay.
all.
Here's a similar question. So, okay, we have a harmonic issue. Okay, granted. Is the power factor going to be elevated because of the harmonics, or is that totally unrelated?
Unrelated.
Okay.
Yeah.
Okay.
Unrelated.
Here's another question. How do you select the best minimum harmonic VFD drive? Which manufacturers offer the best drives?
So I will tell you this without reservation. I do not get any money from any vendor. I don't even have a T-shirt from them. So I'm completely agnostic in this. ABB has as part of their drive has a filter that captures this harmonic energy and stores it and reintroduces it into the drive operation. However, they figured out how to do that, and they've been refining it over the years. Those guys are freaking geniuses about this. Their drives are way more efficient, and you can see that if you look in their manuals very closely, you can see what the power requirement is for 50 horse ABB drive compared to the others, and you'll find out that their power requirements are a lot lower. Yaskawa puts a input line reactor on their drive, and Danfoss provides it to you sometimes as an option. Depends on the size of the drive for Danfoss, and sometimes it's an option that you can select or not. So I would just be, and there's a bunch of others like JCI and several others that make drives, and so I would, if someone gave me a price on a drive and it was way low, I would say, hey, does this have an input filter on it? What is the input filter? Can you describe it to me? And very often you'll find out that it's not something that they produce as a standard item. They don't offer it as a standard item.
Okay. Just
So
one question is more of a statement, but you might be right. I guess I glossed over it. So the load factor equation is I believe it's kilowatt hours divided by kilowatts times number of hours in the billing period. And that's if you're looking at it as monthly bills, and I assume that's what you've got. But
yep.
I think in your equation, or at least this person's suggested, maybe you missed the number of hours in the bill. I don't know. So I usually just do kilowatts times 24 hours per day times, I say 30.4 days per bill, because that's an average month is 30.4 days.
Yeah, and it used to be like 15 years ago or so. It used to be the billing periods were really irregular. They might be 40 days some months or 20 days on other months. But that hardly happens anymore. These guys are pretty hungry about getting their money, and they're pretty regular, right? They don't mess around. It's might be 32, but it isn't going to be 33. So
okay, here's one with the rated wire and upgrade. Oh, let's see there. Oh yeah, there's your consumption over billing days. Yeah, right there. Consumption over billing days. Yeah, over 24. You had that there. Divide by billing days, divide by 24, and then divided by kilowatts. Okay. Oh, I see. So yeah, you did it. You just did it in 2 steps. Okay. So here's a question. With the rated wire and upgraded shield for the VFD, what is the estimated savings of using this compared to a typical VFD? Well, that's I guess you can say in terms of percentage of load. I guess you can give it that way. I'm not going to say this many kilowatt hours, but you can say this percent of connected load, maybe. Does that make sense? What his question was?
So basically, you're wondering if you can get a VFD that produces harmonics, and
and compare it to a good one,
and use a rated wire, VFD rated wire to get rid of it. And is it? Yeah. So the rated, let's talk about that for a second. So the increased cost for using VFD wire is something in the neighborhood of about 3 or 4%. It's pretty small. You know, on a typical, say, a 50 horse VFD, it might be, you know, it might be an extra $20. Might
Okay.
might stretch out to 22, but not 25. So you know, that's kind of the difference. Um, you know, I understand the question, and I understand the economics of it. It's not a choice I would make.
Yeah.
But that's it's possible to do that. And sometimes, you know, if you're looking at a VFD that's a problem, you know, maybe that's a choice. Like, hey, maybe that's the only thing you can do is rewire them. Sometimes that's maybe all you can do. Depends on how much room there is in the MCC. Maybe there's no room for
Well,
a choke.
why even bother with that? Why not just put a darn choke on it and you're done?
Yeah, I would do that.
Okay.
Just put a choke on them. Yeah.
How do you size the choke?
So that the choke is almost always going to be sized based on the size of the wire. So you're going to want a choke that the inside diameter for that choke is going to fit around that wire, and I mean fit. So yeah, you know, like, hey, looks like that wire has a sock on it. So you want that to be occurring, and so that limits the inside diameter of that choke. Sort of the way chokes are made, the inside diameter kind of affects the size of the choke and the thickness of it. They don't come in various thicknesses. So you find the choke that fits the wire and put it on and away you go.
Okay. What's the best? Which option? You gave us several options, and I've been talking about chokes because it's cheap, and I'm just that's how I think I'm cheap. Which option do you think is the best overall value for reducing harmonics? Is it chokes or is it these other things?
So you know, chokes are going to be cheap. They won't do quite as good a job as an input line reactor. So let's define quite as good. If I've got a 20% harmonic, a choke is probably going to get me down to 5%. With an input line reactor, I can get down to 2%. Ferrite, you know, on a 1,000-ton chiller, I'm going to spend on ferrite chokes. I'm going to spend I don't know, $500-600 of material. On an input line reactor, I'm probably going to spend about 15,000, but I'll get the extra 3%. So now on an active filter, according to the active filter guys, they can reduce the harmonic down to less than 0.5%. Well, yeah. Anybody here who is involved in soccer, I would just ask you how many, or hockey or something like that, how many goaltenders you know that have never ever allowed a goal? Not many. So that's the active filter question I always have. As they wear out, they tend to allow more of that harmonic energy to pass through, and they get hot and you know things like that. So I'm not a big fan of active filters.
And the chokes don't wear out. They're good forever, correct?
Active filters do wear out.
No, the chokes. The chokes don't.
Yeah, the chokes just sit there. There's an iron core, you know.
Right.
You know, I suppose the insulation on them might after 15 or 20 years or so, the insulation on the outside might get a little stiff, and you might have to spend another $500 to replace them. But maybe, you know, I even doubt that. It's only 100 degrees or so.
Right. Okay. So energy calcs for equipment replacement, like let's put in a new chiller, let's put in new package units, whatever. Do they account for reductions? Do they typically account for reductions in harmonics? Or do you think there should be specific studies, harmonic studies done to calculate the additional energy saving by replacing it?
They typically don't, those calculations typically are not done. As a rule, JLL is very recently saying to anybody who is putting anything with a VFD in it in any of our buildings, better have a harmonic filter and prove it. So we are forcing the issue because we see that. We see the result of that.
Okay. It's funny, all the people asking questions have left, and most of them, but there's still a whole bunch of people here, the ones that didn't ask questions. Okay. Is there a specific equipment we should be looking for in a hospital environment outside of central plant building systems? Oh yeah. Yeah. So what is like radiology, MRI machines? What in hospitals are typically causing harmonic issues?
Yeah, anything with high, with a lot of electronics in it, they're going to be have a lot of those are high speed switching devices like an MRI or an X-ray, anything in radiology. Any of those things are producing a large amount of harmonic energy. And yeah, you'll see it at the MRI and you'll see it at the X-ray machines, radiology, things like that. And if you put a choke on the power feed to that, you're not going to affect it at all. They won't even know it's there.
Right. Machine won't know. Yeah.
Sure.
Right. Because that's a machine you don't want to break. That's pretty expensive. Okay. Does lowering the harmonics lead to a lower build demand?
Yeah, power meters are when they measure demand and power factor particularly, they're just looking at phase angle, and so they don't even care about kVA demand and consumption these days. Like in the last probably 15 years, they stopped doing that. They just look at phase angle, and they do some stuff there. For kVA demand, it's a different kind of calculation in the meter that it's not really affected by harmonics. It's just not. So just to kind of go take like a minute to explain this. The old mechanical meters were, if you went back and way back in that time machine, the old ones used a spinning disc with a little line on it. And the more power you use, the faster the disc spin. It was an aluminum disc. And it had an optical counter on it to measure the speed of the disc, right? So if you had a harmonic or various things going on load side, or even on the supply side, they would all kind of work together right at the meter, and they would cause the resultant energy would cause that meter to speed up or slow down as the sum of everything that was going on around it, right? And now the problem with the spinning disc deal is that they couldn't report anywhere. You couldn't get any remote data. Well, when electronic meters first came out, everyone went, hallelujah, I don't have to have a meter reader. But very first versions of those did a very poor job of measuring a time slice of a 60 hertz waveform. They were only measuring it of a 60 hertz waveform. Maybe they only were measuring like chopping that up in 50 slices, something like that, 50 or 60. These days, to get that granularity so that it can, so the meter can operate the same way the old mechanical one was. Because what they used to do, they used to test the old mechanical meter against the new electronic one, and the old mechanical meter was always more accurate.
Right.
And so the meter manufacturer got more and more and more intense about measuring a smaller and smaller time slice. Now it's measured in takes the 6 years waveform and it chops it up into 100,000 pieces, very 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 small. Well, great. It does a good job competing against the mechanical meter, but it goes for the head fake of a transient or harmonic voltage, and it reads all of that stuff every single time. And from the utility's point of view, utility would look at that and say, well, this isn't bad. I get more money, right? But they might get really nervous about it or get really anxious about it if you were causing so much trouble in your site that your neighbor is having a problem with harmonics. That happens a lot in residential applications. Because you might have 50 houses on one transformer.
Here's a question. This one's probably a bonehead question, but I mean, so when I say bonehead, that means it's coming from me. So That is, okay, let's say I have 3 wires going to a load that I think is causing a harmonic issue. I put the choke on not the ground, but the other 2 wires, on both wires, not just one of the 2, right? I put a choke on both. Is that correct?
You put it on if it's 3 wires, I'm assuming that's a 120 volt device.
No, not 2 wires,
So
3 wires.
you would put it on
3 wires, 3 wires.
a 3-phase device or a single phase device.
3 phase.
If it's 3-phase 3 wire, you want to put it on all 3 wires. If it's 3-phase 4 wire,
Okay.
you put it on 3 and don't worry about the neutral.
Okay. Okay. Good. That's good. That's good. Okay. Here's another one. Would it make sense to install a ferrite choke preemptively on equipment that typically causes harmonics, like chillers, pumps, etc., or will the chokes cause issues if there's no harmonics present? Yeah, that's a great question. And actually,
No.
I guess, and in addition to that is, you think that if you're an ESCO and you're doing this for clients, that's probably a smart thing to do if they're going to be measuring the utility bills and looking at savings that way. But go ahead, answer.
Yeah, and it is, from an ESCO point of view, I would do it, especially if I knew the equipment was, if it was a chiller, I would do it for sure. So on a regular hertz signal that does not have harmonic, the way the electrical code is written and the way the wire is sized, the insulation on the wire and the conduit are enough to deal with the magnetic force that's generated by that conductor. And so you're not gonna, if you put the choke even around the wire, you're really not gonna affect the 6-Hz waveform. You might slow it down by like a fraction of a percent, but the insulation is made, the spec for the insulation and the spec for the wire are the result of that is that the EM energy is just not strong enough to get outside and cause a problem. And the choke really won't even affect it at all.
Someone asked.
That should give you an idea of what happens when you do have that harmonic energy, how much that harmonic energy does affect that EM field around that conductor, which is what you were describing you felt. If you get a millibus reading of 3500, I guarantee you're going to feed that. You're going to feel it. You're going to feel it standing there. Your hair and your arms will stick out. You'll be like, I'm going to glow. What am I going to? It's not bad for you, but you'll feel it.
How do you input line reactors? Do you need licensed electricians?
Yeah, for input line reactor, you would. Yeah.
Okay.
Yeah. And I would say that if you're going to put a ferrite choke on, you really want to have an electrician do that. Have a site electrician go in and do that. And here's why. So I used to, once upon a time, to figure this out, I used to actually put on a Cal 1 suit, shut down the electrical equipment, go inside the MCC, put a power quality meter on, close everything back up, power it back up, and take off the Cal 1 suit. I stopped doing that. And I stopped doing that because after a little while, like recently, say in the last 8 years or so, about half the time when I open up the MCC panel, there's parts for the MCC panel lying in the bottom of the MCC bucket, hold down bolts for the bus bar, things like that. And so when I see that, I just close up the MCC panel and say, I'll come back when you get your installation finished. I'm not touching anything in here. So it's the other reason why I like doing it this way. I'm external. And so if you get an electrician to go in there, he's going to go in there, and but if he sees a problem, he's not going to do anything until the problem's fixed.
That's right.
If he's got a bus bar that hasn't been completely assembled, he's going to say, hey, stop before we do anything else. Let's get the bus bar fixed up. Stuff like that. So
okay, this is a great question. This next one. I mean, not that the last one was great. This one is it's great because it intrigues me, because this is the way I would want to do it. So Chad's asking, is it better just to put it on the mains or on the specific load? Why don't you just put it on the mains? It's like, yeah, it's data center. Yeah, we'll just put it on the mains. Forget it. We're done. One. I don't have to measure anything. I just put it on. What's it going to cost me? $1,000? Who cares?
That's a great idea, but you're going to run into a practical problem. So you need space around the conductors for the ferrite chokes to go on. You need physical space about
Right.
on a typical MCC, you need like an inch or around the outside. When you get closer
Right.
to the main, you need more space on the sides. Plus, you need the length, exposed length of the wire, and that is very often a big problem. So, you just run into a geometry problem. So,
That's a
and
great.
besides, like, if you go to shut down the main, you'd want to shut down the main to do that. That's a real
Oh,
pain. So shutting down the MCC is not as bad. So
okay. Yeah. So it's not one per plant. It's one per piece of equipment in the MCC, right? Okay. So
yeah,
what about LED lights causing harmonics? Yes. So they could do it, and it's just the same thing. You just put it in the lighting panel if you notice it. I mean, guess you could use your Gauss
yep,
meter and figure
yep, yep.
Uh, okay, large site with one electric meter. Will individual buildings harmonics? Oh, yeah. So you have a military base, let's say, and they're all the buildings on one. Why not just do one? But it's the same problem, right? It's the same problem. There's
Right.
not enough room to put the thing. Okay, it was a great question.
That energy that's generated, if you really don't want it getting into the electrical system and causing a problem with the neutral or the ground wire, the closer you get to the source, the better off you are. The further away you
Hmm,
get from the source, the more likely you are to have that spray out into the rest of the
hmm,
electrical system. So
okay.
I've actually had a building in San Francisco that shut down because of this. It's the San
Hmm,
Francisco Federal Building, and they were shut shortly after they opened up, probably about 3 months after they opened up. They were shut down for a week. The elevators didn't work. The fire alarm system was going off. It was a freaking mess. And so you want to try to treat the problem. So not band-aid it.
Is there a way to directly measure third, fifth harmonics and fine tune the filters?
Yeah, the input line reactors will do that. Input line reactor will do that for sure. You can pick specific harmonics and you can even use a transformer. You can use a regular transformer that's designed for that particular thing. So yeah, there are ways to do that.
All right, I think we're done. That's it for questions. Dwayne, that was great. I learned a lot. And that was great because this is so simple. All you need is a Gauss meter. I mean, that's what I call it. You call it something else. What do you call it? A magnetic field meter or something?
EMI, but it's milligauss. You're measuring milligauss. Yeah,
Yeah.
classic fix, right? Like I buy a tool on Amazon and it makes me smart. So
Yeah. Gosh, it's so simple. And calculating the savings is so simple. I mean, you're estimating. You don't know what the power factor really should be, but you can make an estimate based on building type. So,
right,
yeah, that's crazy.
right. And if you really wanted to get very exacting about it, you could do before and after measurements after you put the choke on or the input line
Yeah,
reactor. If you really
yeah.
wanted to get like super accurate about it, you could do that. You can do that. It's not a big deal. So and we're actually doing that at a site in New York. So no big deal.
All right. Well, thank you, Dwayne. That was really wonderful.